All right, so I know I've been a little lax with the polls the past few days because they've been a little bit different, but I actually do have a poll today that I'm going to ask. I'll give you a little bit of time though. It is the last week of class, I know, and so it's a bit hectic. So I'll give people a few minutes to show up. The poll is actually, this one actually matters, your selection. So I'll preview the question for everyone here so you can see it. But the poll is going to be about the final times. So right now, the final, I'll close this. The final right now is scheduled for 8:30 a.m. to 11:30 a.m., which if you have to pick a time to spend 3 hours watching these things, it's not the best time, I know, for many college students, or be they undergrad or master's students. So I actually, unfortunately, there's no room available that can hold the entire class before 8:30 p.m. That's when the finals are over. But depending on your preferences, I'll open this up in a second, but depending on your preferences, many people might prefer the 8:30 p.m. time to the 8:30 a.m. time. So I'm going to have that as a poll and see people can see. The alternative actually is we could have something a little bit earlier in the afternoon or in the evening as well, like more like 6 or so, but we have to be split over 2 different rooms, so it's not ideal either. So I'll open that up in a second, but it actually will be a it will count to answer that question, but answer with the one you actually prefer. I should say, if anyone has, if we go with a later time, and you've already booked travel to somewhere, you know, that was your last exam, and so you booked travel after, that's fine. You don't have to worry about it. You're free to miss that one then, so maybe it's beneficial for people that do that. But you have to also view the videos. So once we have the session, we'll also have a YouTube playlist that will list them all, and you will be assigned certain ones to actually review. We won't tell you the order, so you can't just skip through. Hopefully you can't just skip through and find them. You'll still be responsible for your reviews no matter what, so you'll have to watch them at some point. It's really honestly a lot more fun if you just do it here. I guess you can't watch in double time here, but it's a lot more fun if you do it here, honestly. There'll be some sort of either pizza if it's in the evening, or I guess coffee and something if it's in the morning. I don't know. I'll open it up in a little while, and we'll sort of see what people prefer. I got the impression a lot of people would prefer not 8:30 a.m., but we'll see what people actually say. If the alternative is 11:30, though, and I should say you'll be excused if you either have a final the next morning at the 8:30 a.m. or if you've already left that time, because you know it's understandable either way. Okay, so today actually it's going to be a slight change of schedule from what the schedule says. We're actually going to just finish. I think actually it'll take most of the rest of the time to finish through the data science walkthrough. I think it's kind of actually a valuable lecture as well. I don't put too much value in doing this kind of stuff too much, because seeing me write code in real time is not the most efficient use of most of the time. But seeing it a little bit is actually can be useful. And this is more or less. I mean, obviously it's a little bit scripted now because I did work on this ahead of time and I'm just typing. But this is more or less kind of how I kind of go through problems like this. And so hopefully it helps you sort of see how I've gone through a task like this. Okay, so if you remember when I left off, and I'll actually pause for questions in a second, but when we left off, we sort of had this notion of trying to predict the classification of these different, we tried to have a game where we predict the relative ranking of 2 different items, right? And it turned out that game was pretty hard for us to do. I've tried a lot more than just this too, and I'll just let you know that this first game of given 2 random items here, pick one is higher, I do a really bad job of getting this one. So you know, this was one here. I guessed, for example, it was number 1 was the better toy. They're pretty close, but actually number 2 was a better toy. This one was ranked higher. And so I'll do this a lot, and I'm not much better than random chance. On the next, what we had to do is we had to somehow change the problem in some way, right? And so what we chose to do is we chose to actually change the problem such that we're only looking at the bottom 10% and the top 10%, because even though that's a very different problem, and I actually do want to emphasize that this is a different problem we are then focusing on, so it is not the same problem, and if you try to apply this classifier to the entirety of the data, there are going to be issues, right? So you cannot just apply this as it is, but we're still trying to do just in our analysis phase, figure out is there any sort of signal in this data we can figure out at all, And in this case, it does seem like this problem is a little bit easier, at least. You saw it. I think I got the first two wrong, but then all the others right after that. And I've run this a lot. This is in fact random here. I'm not pre-doing any of these things, but I think I can pretty well guess. So I think this one's probably better. I can do a pretty good job of guessing these ones or predicting these things. So in general, I think it's a better sign that the task we had here was actually a better one, and one that we can at least legitimately focus on as a method for analysis of this data set, if not, a genuine prediction algorithm for the entirety of all our data. Okay, so let's take that as our task now. Let's take our task being as I am going to try to build a classifier that says, given an object, an item from Amazon, can I predict if it's from the top 10% of all rated toys for this age group, or is it in the bottom 10% of all rated toys from this age group? And that's going to be a classification task. And one thing that I sort of pointed out on many people's project proposals was that rather than try to sort of predict things well, it's often good to look at quantifying distributions of these things, right? And this is actually kind of a restricted but one sort of partial example of that, where we're both looking at a subset of the data, and we're not trying to really predict the actual rating itself. That's a very hard task, and we sort of went through that as a regression task, and it seemed very hard. What we're trying to do instead is sort of make some characterization about the distribution over, really good items and really bad items in this case, for example, right? And so I want to emphasize that that's the kind of thing you should be sort of thinking about if the problem just appears to be sort of just too hard. There are lots of caveats to sort of add there, but this is at least one way of starting to get around some of that stuff and starting to make statements about this data, despite the fact that we seem to be very bad at this task, at least nominally. Okay, so let me now start then some work on classification. So we're going to we've set up our data set, and we're going to sort of do classification. And so I guess the indices we're going to talk about are all the ones with the Bayes rating greater than the percentile of, I guess, the Bayes rating. So all the ones where the Bayes rating is percentile is greater than 90, greater than 90, or the percentile is less than 10. All right, so we're only going to focus on those examples where are in the top or the bottom, and we're going to make that a look at the actual NumPy array of this. So this is going to be our data that we care about. This is also, and then y is going to be equal to the Bayes rating. Or rather, sorry, y is our class. This is going to be equal to, is the Bayes rating bigger than the mean or the median? So y is going to be, is the df, the Bayes rating, greater than the median. Okay, all right, so this is our subset, and then our labels for that subset. That's the question. Oops, yeah. That was easy. Okay, so here's our game now. The label is going to be is our rating greater than that. Okay, so let's now do our training set test set split again. Let me just copy the code from the above where I did this before. We're just going to overwrite. We could keep the old one, but you can go back and do cells. This is probably not the best way because now our notebook has to be executed sequentially now, but that's actually better than at least having it be executed out of order, even if it's not perfect. But of course, we're only going to look at the ones that are part of this index set. Okay. Okay, so now this is our new test set and training set. And one thing to sort of note here is this is quite a bit smaller than our previous data. So there are only 227 examples in our training set, and a fair number of features. So this is a small data set we're talking about here. Actually, that seems a little bit small. Did something. X shape. That does seem. So 20% of that. Oh, I get right. So 20%, and then I divide it up into this. Okay, so the entirety of our this data here is pretty small, and then we're further dividing it up into so it's about 600 or 500 or so examples, and then we're going to further divide it up in training set and test set. So our training set's fairly small here. So we're not talking about big data by any means here. We're talking about analyzing a small subset of data to see if we can figure out anything interesting about this particular distribution. This particular subset of data. Okay, so let's now start basically trying to fit some classifiers. And as you typically do, right? You always start with the most complex thing. You never, or the thing that's worked best in the past. So let's import, some complex ensemble methods. So let's do from ensemble. Let's import a gradient boosting classifier. And just because we actually, yeah, I shouldn't have to do that one. Okay, so let's set our classifier equals the gradient boosting classifier, and let's fit the training set and the testing set. And since we, training set, and let's predict on the training set and the cross-validation set. Okay. Okay, so this takes a little while, and we get 0.7 as our accuracy on the test set, and pretty high. Sorry, on validation set, and pretty high on the training set here. So again, this is good, but it's very hard to actually quantify whether this is good or not, right? I mean, we're picking one point of parameter space we just happen to have with our initial hyperparameters there, and this is obviously, it seems very high. This seems, certainly better than 50%, and we know our nominal, and in this case, this is a case where we know our sort of, default performance should be 50% because, or thereabouts. Not quite, because it might be a little different split. We didn't really do stratified cross-validation here, so it could be a slightly different split on the cross-validation set, for example. But we know sort of, we're pretty confident that there's half of our examples are the bottom 10 percentile, and half of them the top 90th percentile. And so this seems better than a random chance, as we would kind of expect. Remember, again, our features here are the TF-IDF features plus the price. Those are our two sets of features. So okay, so let's go a little bit beyond this, right? We want to get a sense not just of sort of this performance here, but how this performance is varying with, are we overfitting here? Since we are, but we just need to add more data. Should we just go collect some more data? How do we sort of avoid overfitting like this? Is it good to collect more data? Do we need to try a simpler classifier? What's our sort of plan of attack here? And you remember in the last lecture on debugging data science, one of the first diagnostics I would always recommend running is plotting the performance on both the test set and the training set, or cross-validation set and the training set, versus the number of samples you have. So there aren't a ton of samples here, so you have to kind of be a little bit you can't have too many here, but you do want to actually look at, is the performance leveled off even under this classifier, or are we still just improving? We don't have much data here, and we just need to collect twice as much data. We should just go back to Amazon and collect twice as much data, maybe on better toys, or maybe I should predict not just the top 10 or the bottom 10, but the top 20 and the bottom 20, something like that. Even though that might be a harder task now. Okay, so I'm going to define some function that will basically get the number of, get an error metric with a different number of samples. So XCV. And N samples. Okay, so what this is going to do is it's going to fit the first, up to the first N samples of my data, and the on the X and Y. And then I'm going to return an array with the scores for both the training set, which in this case is the training set with just that many samples. So this is the score on this exact same thing here, and then the score. Oops, I'm going to have just an array with just these two elements here, and then the score on just the validation set. Okay, so this is sort of a nice little, it'll be a little function that'll sort of tell us, are we to have too much data, too little data, what? Okay, so let's now define a range of samples that we actually want to evaluate this over. Let's evaluate it over, say, 10 different ranges here, basically for. So it has to be a number, the actual number of samples, of course. So we're converting to an integer, and we're going to have this be in this, say, a range between space range between, say, actually, we can change it a bit. Let's say 20 samples and the total number we can have. So this would be a linear interpolation between 20 samples, which is a small amount. You can't probably learn much with 20 samples, and the full 270 or so, which is still pretty small, but maybe we can actually learn something from it. Okay, so we're gonna interpolate that, and we'll have 10 different interpolation points. Say this is their number of samples. Oops. X in lens space. Thank you. And then we're gonna evaluate the errors. So the errors equals get error samples of the classifier. Actually, sorry, it has to be this for another array of samples the classifier x train, y train, x CV, y CV, and n, or let's say n for n in n samples. All right. And also a plot. There's 0. So I've made an array where the first column is going to be that, and the second column is going to be the next one. So the first element here will be the training error, and the second element here is going to be the validation error. And samples, errors, and let's just label it. Well, you can see pretty well. You can probably guess which one's training and validation, but let's just do it anyway. Okay, so this is sort of how our performance is looking. And so I would actually say we clearly are in the regime where we're probably overfitting here, right? I mean, we have as boosting is known to do, boosting here is basically getting perfect performance on the data set, as of course it will, because it's a really small data set. If you have a complex classifier with a lot of power, you're going to overfit to it, right? So we're overfitting to a training set. One nice thing about boosting actually is that despite the fact that it completely overfits the training set, it actually does pretty well in the testing set. So it's actually kind of like it's sort of not like most algorithms you might see because of that. It actually does quite well, despite the fact that it seems to be overfitting. There's a big gap here, but this is definitely improving over just random chance here, which is sort of down here. But I would actually say it's not obvious to me that we really are in a regime where we'd benefit a lot from more data. I mean, there's certainly some noise here. We would sort of get a much better sense of what was going on if we maybe cut this out a little bit and helped a little bit there. But really, it doesn't seem like we're going to hugely benefit here from more data. So maybe going back to Amazon scraping more, it seems like we're improving up to this point or so, up to about 200 samples. But after that, we seem to be, there's obviously a lot of noise here, but we seem to be kind of leveling out a little bit. So it's not obvious to me, for example, that even though we have very little data here, this sort of plot, at least for this classifier, shows it's not obvious to me we benefit hugely from going back and rescraping Amazon for another 1,000 or so more toys to look at. It seems like we've kind of leveled off at performance, with some number, a relatively small number of samples. So actually, that's what we're going to do. We're going to stick with this number of samples, kind of based upon this. But it also suggests where we might be, to a certain extent, overfitting a little bit, right? So we might want to try a simpler classifier. And see how they do. Maybe we don't need boosting over, in this case, TF-IDF features. TF-IDF is something that's we already have a lot of features, right? We have, what did I say? We had 669 features with only 227 data points. So it's really not clear we're going to benefit at all from having a really powerful classifier. Maybe we need something more like just logistic regression that would be a simpler classifier. So let's go ahead and try that, actually. Let's go ahead and try. Let's import logistic regression. Create our classifier with the default parameters for now, and let's do this same thing here. I'll just copy this and see what it looks like. Okay, so now, I mean, it's actually a similar story. We actually are our performance decreases, but this is probably due to the fact that, I mean, I don't want to make too much of this decrease here. That's probably just random noise, right? It's not common that more data will actually make you have worse performance. What's probably correct here is actually we're just training a little bit more data, and so it's actually just obvious that there are some mismatches between a training set and test set, and that's made more clear by the fact that when we include all the data, there's a slight decrease in performance there. We're also evaluating only on one actual set of hyperparameters here, so it's sort of unclear what we might be inferring here. But this to me at least looks a little bit better, right? It looks like we might actually, maybe we even would benefit from more data here. We're not going to do that here, but it seems like these things are converging, and we have a better sense of these things kind of, we're not doing any worse than we were with gradient boosting. I think you saw, right, that it was about like 70 before, and here we're actually getting about that at the end, maybe a little bit higher at earlier times. And so it seems like we actually are benefiting from this simpler model in this case. So let's for now go with that route. It doesn't seem at least like we really need the power of a nonlinear classifier like gradient boosting. So let's just stick with logistic regression and see how that actually keeps us going. But the next thing we need to do is actually analyze the effect of hyperparameters on this performance here, right? So we've just now picked, again, the default values for this task. And it picks, if you look up the default values here, right, it picks, well, I guess the penalty is L2. That's probably fine. L2 regularization, that means that our C parameter here, that's the inverse of our regularization parameter as we defined it in class, the inverse of lambda. That's just picked arbitrarily to be equal to 1. Is that a good value? I don't really know. So let's see if we can actually get a little bit more sense of what's good or not there. So I'm going to create another version of this sort of similar function like we had here, except this time I'm going to actually vary the values of C instead of so our regularization instead of the I call it get error. Instead of the number of samples. So here we'll put C there, and I think that's the, I think CL has a C, yeah. Equals C, we'll fit the whole data to it. So we'll just go ahead and use all the data, and we'll see what those actual scores look like. Right. So this is another important diagnostic. Whenever you have hyperparameters like C or something that you want to fit, you should at least individually be plotting over each one, seeing which one works best. Again, on the validation set, not on the test set. I've never touched our test set yet, but on the validation set, you should be looking at which one performs best. If you have many parameters, you actually want to do kind of a grid search, right, where you look at all possible combinations. Maybe if you can't quite do that feasibly, you sort of look at one dimension, then you look at the other dimension, this kind of stuff to sort of figure out where you're doing well. But this is the kind of thing you actually would want to do. So this is how we're going to get our different values of C. Now, the next thing we want to do is actually evaluate this for different values of C. And remember, when you think about hyperparameters, at least some of them, you're really thinking about logarithmic space here, right? Because the hyperparameters is not going to vary between 1 and 2. It's going to vary between 10 to the negative 4 and 10 to the negative 5. So it makes a lot of sense to use something like a log space here to sort of vary our different hyperparameters. Let's try something like 4 to 4, and we'll do like 50 different settings there. So errors equals get errors C classifier. This is still going to be our logistic regression classifier, but we're setting the parameter C before we fit, so that'll have the different various fits. X train, Y train, XCV, YCV, and C for C and C. Okay? And we'll plot it. And we want to plot it also, of course, on a log scale. Okay. Okay, so here's our plot of how this looks like. So this is sort of exactly what you would expect. So in this regime over here, we have a very low C value that corresponds to a very high lambda value. In other words, very high amount of regularization. C, again, is just the inverse of the lambda parameter. They just choose to use it that way instead of using lambda. So here we're underfitting. And you can also see actually very nicely, this is actually the nominal class breakdown exactly in our test set, or sorry, validation set. So basically, if we just predict it seems like one of the classes is about 55% of the examples, and the other one is going to have 45. So if we just predict the majority class, we get about 55% accuracy. So that's sort of their nominal baseline accuracy, at least on the validation set. As we increase C here, that decreases regularization up to the point where here we've overfit to the data, right? We're getting perfect test training set validation performance, and our test set, or our validation, sorry, we're getting perfect training set performance, and our validation set performance has decreased by quite a bit. And so we actually want clearly to pick some sort of intermediate value. And kind of sadly here for this example, but almost around 1 actually seems to be one of the best settings here, just almost by chance. But it's maybe, maybe 0.5 or something like that seems to be the best. So let's go ahead and actually train our classifier with c equals 0.5. Which, that is to say, it's going to be logistic regression with just c equals 0.5. That's going to be our only thing. We're going to fit the x train and y train, and we're going to, where do I have it here? Just look at these things and see what they actually look like. That sort of seems to be good. Yeah, it seems to be pretty good, right? It's sort of 7.08 or so. And now finally, okay, now you shouldn't do this very often, but I can't help but peek under the curtain a little bit sometimes. And so let's just go ahead and see what my actual test set performance there is. It's pretty good, actually. It seems, it's a little better, actually. That's just, don't read too much into that. Whenever your test set performance is better than validation set, it just means you've picked the lucky split. It's when it's much worse that you can be actually worried you're overfitting at that point to your validation set. Okay, so now before I sort of move on to the next part, I want to do one more thing here and figure out, okay, this classifier is looking almost entirely at TF-IDF features based upon n-grams up to size 3 in the names only of the products, right? So what is it actually doing? How is it able to differentiate between the good products and the bad products? So let me actually, so we can look at that. So the feature names here is, so we had our TF-IDF. This is just the code for this, TF-IDF.get feature names. When you pass the TF-IDF a data frame, it'll automatically, a text string, it'll automatically create this sort of feature names thing. So this is actually a useful thing. And then we'll also have this feature called like price, though I'm going to call it price like this because it turns out there actually is a feature called price in these names. So we're going to have that. Oops. And we're going to figure out now what is. Let me actually do, I think I want something like this. Plus, do this. Yeah. Okay. So these are our feature names. Now I want to find what are our most important features in some sense. So I want to sort. So I can get this by saying if I have my, what was it called? It's called coef is the name of these things. And so self.coef0, I believe, is going to be the weights of all the different items. So it's just coef is actually I think it's a column vector. So there's only one item. So I'm just going to select the first element there. That's just an array of all my weights that I've actually learned from my classifier. And so I'm going to sort a zip of the feature names. Names of coef. And the key is going to be the absolute value of the actual coefficient. Right, so I'm going to sort by the absolute value of the coefficient because if it's positive or negative, I want to know that. And I also want to reverse this. Okay, sorted. All right, and let's look at like the 20 most interesting features. Oops, feature names. Okay, feature. There we go. Okay, so here are the most important features in our TF-IDF things. And remember, positive means it's more likely to be a good toy, and negative means it's more likely to be a bad toy. And so the most negative feature is bath for a toy's name. And then after that, you have a lot of brand names. So Green Toys is a popular, Toys, Fisher, Fisher Price. Fisher, Price, and Price, they're all, I guess, good. I don't know why it quite picks them all. I guess it's L2, so it actually will just put them all in with a marginal weight because they always occur together. Frog is the next bad one, did you see? And then you have things like Imaginext is also a brand name, Doug. And you have Doug and Melissa and Doug, that's also a brand name. I guess packs are good. People like packs, and there's Melissa and Doug. I don't know. I think this is also a brand name. I've never heard of that before. That probably is a bad thing. And water is a -1. So you see a pretty obvious pattern here where things associated with baths, like frogs and water and bath, are all negative weights, and brand names are all really positive weights. So this is super interesting, actually. Okay. So I have to say, sort of as a parent, this makes total sense because baths aren't fun for a lot of kids, right? And you get them bath toys hoping they're going to like the bath. But of course, you give them the bath toy and they still don't like the bath. And so you're going to rate it negatively on Amazon because despite your investment in this toy for the bath, they still don't like the actual bath toy. Or they still don't like their bath, right? And so this is actually, I think, actually the main, probably actually the main data science takeaway you're going to see here. We'll do one more thing, but this is actually the main conclusion that I could draw, which is a really cool insight, I think. It basically says that on Amazon, reviews for kids' toys, I think, are biased toward, if you give them a toy that's just like a Fisher-Price toy, it's a toy they can play with, of course they're going to like it, right? They're going to have fun doing it. If you give them a bath toy, they're not going to like the bath. And so all these, so the reviews you have are actually really not about the toys themselves. They're about how much is the kid going to have fun in the situation where they actually play with that toy or not, which I think is actually a really interesting insight about sort of the bias people have in reviews, right? So baths are probably not always bad, and they're not normalizing by the fact that baths are already bad and maybe the toys make it a little bit better. They're just absolutely rating the sort of overall experience that kids have when they play with these toys. So I think this is a really interesting insight, and something that I hadn't actually expected when I was first doing this, but it makes total sense kind of in retrospect. So I thought that was actually quite cool. Okay, so and as I said, that's actually going to be the main, or one of the main takeaways from this this lecture here, and we can kind of maybe even stop there. But I want to do one more thing before we do that, which is look at the images as well as just the names themselves. So okay, so let's actually before I do that, I've been talking for a while now. Are there any questions? Yeah.
While we were deciding the classifier, we went with boosting first and then went to a simpler one.
Yeah.
So can you be sure that the results of the Gaussian boosting are just good enough, or should we do have a tuning for that as well and then move on to it?
The question was, could we be sort of confident the results we had with boosting were good enough? Was that the question? Yeah. So they weren't very good here, right? They weren't all that great here in this case. And it seemed like from this plot, we seemed to have pretty good sense that we were just plain overfitting with boosting on this data set. The training error is essentially 0. It's decreasing slowly, but we would need either a lot more data or something in order to make this better. I mean, we could try reducing the complexity of the boosting classifier, but that doesn't really work here. And the bigger point is that also with a model like this, you don't have this sort of nice interpretability of the features as just weights on the linear classifier. So I don't want to make a too deep a statement here. The reason why I did boosting first is because I know that's what people do first. They just try the thing. Boosting works really well like on Kaggle contests, right? So you're just gonna try boosting the first time you do it. That's why I did it too. I actually wouldn't really do that first, to be honest. I would try logistic regression first, or linear regression first. And then only go to a more complex one. I mean, actually, you should try the more complex one too, right? Because there could be a chance that it will just substantially outperform the linear classifier because your problem is just not linear. If you see that you clearly cannot even fit the training set, especially if you have high bias, right? So especially if your training error is not that good, then you should definitely try the nonlinear classifier. So you should try them both. But in all else being equal, and in this case all else is equal, it's far better, I think, to go with a simpler classifier that actually has some simple meaning like a linear combination of the features rather than a pretty complex combination of decision trees was what it boils down to. You can, and again, I was sort of doing that only to show the fact of what most people do, not what I would recommend you do. So you should try both, but then you should see how they both perform and only go with a more complex classifier if it substantially outperforms what you can do. And by the way, I mean, I could certainly tune that to do just as well. I could tune different parameters there and do a big hyperparameter search to do just as well as my linear regression. But I just don't see any point in doing it. It's really unclear to me whether you can gain anything from doing that. Any other questions? Okay, so let's do the next thing now. So remember, in addition to the text we have these nice pictures too, right? So we have these fun pictures of all our toys that we scraped from Amazon that we so diligently extracted from Amazon. And you know, while we've seen that you can remember, so this is the duck, and it was the bad one, and the little baby monkey was the good one, because it's a bath toy, and that one's not a bath toy. But is there? The question is there something else, right, in the images themselves that might be interesting here, right? Can we sort of divine something from the images themselves about how good these things are? You know, so forgetting the text for a second, we just look at this image and say, look, these two things are this is something and that's something, and which one's going to be better from just images alone? If you were being really diligent here, you should probably run the experiment yourself and see if you can do it again, but I'm going to forego that this time and just go straight to the actual analysis. So let's talk about image features now. So again, what I advocated for in data science is not to do something sort of very detailed here, but just to literally take the output of a deep classifier, like a VGG network, like you're doing on the homework, and just use those as features, sort of black box features for an image classification task. So this is what I actually did. I did this. I don't want to have the code for that because this is actually exactly the code in the homework, so I'm not going to write how I did it. But I am going to just open up the features that I created using the few lines that you'll see in the homework or when we have the solutions out. And so I just dumped that to a file called image features. And I should say, I actually, one point I meant to make is these files are now up on the website too, so you can download these files too. I'll put this newest notebook once it's done. And I'm just going to load the image features. Load F. And let's just say x equals x image for now. OK, so just as a sanity check there, I think I had, oops. I think I had that many elements in my data set, and so, I mean, I did this separately, so you have to trust me that I, in fact, exported them all correctly. But these are going to be the corresponding VGG features for these images. And you remember VGG, this is the last layer of VGG before the actual final classification layer, and there are 4,096 different features in that last layer. So this is a lot of features, by the way. These things only work with that many features because you do highly regularize, so you heavily regularize your solution, and it actually seems to work pretty well. Despite the fact that they are so many features, you could actually combine them, one more time, maybe do one more thing of max pooling or something like that in your network. But we're just going to use all of these. These are just kind of the standard VGG features. We're just going to use them all. OK, so there's my X there. And now I'm going to do the same sort of thing I did before. So let me just do this training testing split code that I had before. Again, I'm going to focus only on the task of the top 10 and the bottom 10 percentiles. And let's go ahead and let's just start logistic regression here. Let's not worry about the other ones. Fit. And where do I have this? Let's print them out. OK. OK, so we're clearly fitting our training set perfectly. That's not surprising, considering we have 4,000 features now and 200 or so, 277 examples. But we seem to be doing quite a bit worse on our validation set. Of course, let's see, again, we're just sort of picking one kind of set of parameters arbitrarily there. Let's see actually how we really want to do this by looking at the same plot we had before. So C, I think actually I can just do that. I think I have the same C, but I'll just copy this over. C equals log space here. And, sorry, something. OK. And let's see what this looks like. This takes a little bit longer because we have to now fit to a larger set of features each time. But it shouldn't take too long. OK, I actually might need to go even lower here. I think we're not actually to the point where we're that small yet. This isn't looking too good so far, right, by any means. Let's see what this looks like now. But we're still doing better. Like 66 is still better than the absolute baseline of like 55%. So maybe we're doing OK. OK, so this plot now looks reasonable, actually. So this is another important point. The range of hyperparameters you select is, of course, depends on the actual features themselves. So in this case, we picked some new set of features, and so therefore it's going to not quite match up with the old setting. But what we also see here is that it doesn't seem like you get that much higher than like 63% or so. But it's something, right? It's not nothing. We do seem to be able to actually glean some information out of these images that we didn't get with, or sorry, that we are doing better than just random sort of chance here. And so maybe, but importantly here, what's sort of different than here is the actual hyperparameter you want to use is actually quite a bit different, right? It's probably like 10 to the negative 4 or so, maybe 3 is sort of the best value. So let's do c equals negative 4 or something like that. Okay, so marginally better than the 0.6. Let's go ahead now and see if this does any better actually on the test set here. Okay, and 5.9. That's not great, but it still seems better than just random chance, right? So maybe there is something in these images that is actually valuable here. And so the question that is important to ask now is, it does seem, once we have this, that we actually can predict something better. These are going to be harder to interpret, so I won't bother sort of talking about like what are the best ones here, or you can't really do the same thing where like what are the best words or what are the best images. You could look at the sorted list of which are the best images, but that isn't all that helpful. But the important point here is this does seem to be giving us some amount of predictive accuracy, right, above what we just get from baseline. We know the baseline here is something like the 55% you see here, and it seems to creep up a little bit. Obviously, we're overfitting, when you get to this sort of section, but right around there seems kind of like maybe we're learning something. So that's good. We could also, by the way, look at the scores, so we can actually predict what the scores are of the. Let's say if the trainings, or no, it's not the training. Let's do the cross-validation set. And let's see. Let's look at what the image. Actually, how do I do this? Okay, df. Actually, I need to do something like this. Df. Actually, this is going to be a little bit tricky because I have to figure out here where the this cross-validation set is in my entirety of my set to display that. You know what? This is actually was going to be a kind of a. I didn't glean that much from this, so I'm not gonna do it right here. I want to make sure we finish in time. I'll go back if we want to. What you can do is you can actually look at the scores that are predicted for these things, and then look at what the images are that actually get top scores or low scores, and see if there's any insight that you can glean out of that. But I'm actually not going to go through that right now because today I would have to just sort of figure out where in the full data frame these indices are, and I don't really want to do that right now. Because I created it not by knowing myself, but just by doing this train test split, which I kind of want to just not worry about too much right now. I guess I could do that on the whole thing. And then the whole thing, yeah, I could do it on the whole thing, but then it's going to just put the training set at the top. So let's not worry about that for now. Okay, so let's actually move on to actually a much more important question, I think, which is, it does seem like we can gain some information out of these features, right? That does seem to be the question, be the case. But the bigger question is not just can we gain some information, but can we gain any information above and beyond what we already have from the text itself, right? Because ultimately, it doesn't really matter if you can get, we're already getting much lower accuracy than we have otherwise. So why does it? It's not really important to get the 60% here. What's really important is if I add these features to my other classifier, will it actually make it work better or not just does it work okay by itself. All right, so what we really want to think about is these sort of images and text. All right, and so what we're going to do there is we're really just going to combine our image features and our text features, right? So we're going to basically create our X, which is going to be the stacking of the XTF IDF. The image features and this log feature on the price. I don't actually know if that one's useful or not, but I've just left it in this whole time. Okay, so we can do that. It's the same. It's the right sizes. Everything's sort of the right sizes, etc. But there's actually a really important point here that I want to emphasize, and that is that doing this by itself is actually not a good idea, because the problem here what you can kind of see from this plot here is that these two sets of features require very different regularization to solve, to sort of come up with the best solution, right? And the reason for that is that these two different sets of features have very different norms to them. They're basically, these ones might be scaled by, say, 100, and then if you scale features by 100 and regularize, they're going to have very, you're giving an advantage to the features at the bigger scale. So if I just run this, basically what'll happen is it'll only pick the image features, and we'll get performance kind of on par with the image classifier before. I hope that makes sense, because that's actually an important thing. This sort of notion of combining features is a really important one, but you have to make sure they're on the right scale when you do so. Now, importantly, we also, though, don't just want to normalize these features kind of as they are. TF-IDF, say by dividing all the columns to have to all the features to have unit mean or something like that. Zero mean and unit variance. TF-IDF, by its nature, the whole point of TF-IDF, right, is that it puts less weight inherently on things that occur more frequently. Similarly, the image features that come out of V2G, they're very well calibrated to be the ones that are bigger or the ones that are more important. So we don't just want to go and normalize all these things and throw away all that information. What we can do, though, is normalize the entirety of the features. So if you look at the norm, and I'll just print out both of them. This is going to be the Frobenius norm, which is the sum of entries squared, the square root of that thing, of the TF-IDF features. And yeah, if we print that, and then we look at, let's do them both. The image ones. We see they vary by about a factor of 100. So the image features are about 100 times more powerful, and they also are a little bit less useful. So I'll just go ahead and divide these by 100 approximately to put them on about the same scale. So this is going to be, if you don't do this, by the way, this won't work at all. You'll just get the same performance as just doing this. So if you have multiples of features, in the big picture, you probably can do something more like feature selection or something a little bit fancier. But for a first quick pass, if you want to combine two sets of features, try to make their norms kind of approximately equivalent over the entirety of those features, especially if they're ones where you don't want to just go ahead and normalize them. Okay, so this is going to be my X matrix there. Here is my all other things, and now I just do the normal trick we did here. I can even probably copy the code verbatim here. Let's just do this. Let's not worry about fitting it one time. Let's just fit it for different values of C. Since we divided, we probably will have something more like our old space we dealt with, so maybe like 4 to 4 and 50. Okay. All right, so that's nice. So we're getting, actually, we were about like 70 before, and here we're seem to be getting a little higher than that, right? So let's this is about at maybe, I don't know, 0.02 or something like that. That's hard. I love that. No, it's more like 0.05. So let's see how this does on everything when we actually try it out. 0.5. All right, and lo and behold, we actually do increase some marginal amount of points. We had like 7.5 on the test set before, and now we have 7.8 0.78 on the test set now, where we had 0.75 before. So it does actually appear that in this case, again, modulo the very small data you have here, which is which is a big caveat to all this stuff, and the fact that this is not the actual distribution of our data. This is a very skewed distribution about just the top ones and just the bottom ones. It does appear you actually can infer a little bit more out of the examples. Having said that, I'm actually going to not do that for the rest of the time. I'm just going to look at the classifier that is just going to use the other ones, because I realized I actually didn't extract image features for my original goal. My original goal, right, was to find, if you remember, was to find the best reviewed toys, the best toys to buy, my kids that do not have very many reviews yet, right? So this was only on the data set I've been talking about so far was only the ones that had more than 4 reviews, and the other ones I'm going to talk about are going to be the ones that have less than 4 reviews, because I want to find the best of that set. And I'm going to basically build this classifier on those. Unfortunately, I forgot to extract the image features for for that entire data set. But the reality is, this is maybe a 0.3% increase. So, my kids will only be 3% less happy, I guess, is the lesson from that. Okay, so let's do the final thing we want to do now, which is just finding the best under-reviewed toys. And as you can imagine, you might be kind of disappointed in the results you're going to get. Maybe the results you saw before might key you in on that a little bit about what's going to actually happen here. But let's go ahead and now, remember I down selected, I think, here to the ones, where did I do that? I guess I down selected here to the ones that, where did I do this? Somewhere I selected only the ones that had more. Yeah, here we go. I down selected the ones that only had more than 4 ratings. So I'm going to do the opposite now. I'm going to select only the ones that have less than or equal to 4 ratings, and that's going to be like my deployment classifier. So the important thing is, in that case, what I'm saying is I don't really know the true rating, right? I'm saying that the rating in these cases are just sort of, there isn't enough information to really go on. We only have 3 or 4 reviews. They're just too noisy to really say much. But we're going to go ahead and try to apply it to that, and then maybe not verify if we're right or not, because we don't have enough data to verify if we're right or not, but just evaluate, what are the best toys? Which toys should I go out and buy now? This is actually, by the way, how machine learning is often deployed in practice, right? You first build a classifier that's just on your training set, and then you apply it to some new data, and you have to analyze that new, and you don't want to just have it be that, right? Maybe you could, but typically you apply it to some unlabeled data set now, and you want to do some sort of qualitative analysis on what's actually happening here, right? So you don't want to just sort of say nothing and say, yep, here's the classifier, 100%, this is the one to go with. You want to say something like, qualitatively, what is this actually doing? And you might have a pretty good guess of what this is going to do from what we saw before. But okay, I'm going to reload now my data frame here. I'll call it something else just to have that. I actually had to do a little bit of tweaking, so I'm going to find also, I had to do a couple of things. I normalized a bunch of features, so I still have to do that kind of processing. So let's see, what did I do? I did this. So I first, the number ratings have to be a float. So I wanted to replace those, make it a float and replace the commas with nothing. Make it a float. Take the stars and I guess I didn't do that one so much, but I'm going to just do it anyway. Okay, so I could do all these with my new kind of full data set. But instead of dropping the ones that have fewer than 4 ratings, I'm going to drop everything else. So my deployment data set is going to be equal to only those where num ratings. Let me just do this before. Okay, only those where num ratings is less than or equal to 4. And I'm going to copy that. All right, and I am using the price as a feature, so I have to drop the ones where the price. Remember, there was a subset where the price was not defined, so I still have to drop, because you have to add it to your cart to find the price or whatever. I still have to drop those, or things won't work. Okay, so now I have my deployment data set, which is very different from my other one, right? This is only the toys that have fewer than 4 ratings. All right, so there's obviously a different number of those and everything. And now I'm going to go ahead and create my features for my deployment. I'm going to deploy my classifier. So this is going to be, in this case, I'm going to only, because I didn't extract the images, I'm only going to take the IDF transform of to array. Now, importantly, there's actually an important point I want to highlight here. I need to use my old TF-IDF features to transform my new elements, right? So if I just create a new TF-IDF object on these ones, those indices, of course, are going to be completely different from the indices that I actually trained my classifier on. So I've built a classifier already. I want to just use that classifier. So therefore, I need to use the same features. I need to create the same features that I used in my previous classifier. So the way to do that is to call the transform function on my TF-IDF object. All right, and then what else did I had? I had this like if deploy price, and then I get the values from that. Okay. Think that's what I want. I realize also, so X should have those 69 features. I actually am going to have to rebuild my classifier because I wanted this one. Let's see. I want my one without image features, of course. So I want this one. What did I do? Did I create this? Okay, I'm going to have to redo all of this now. Some weird copy. Okay, hang on. Okay. All because I created these things in the wrong order. This is why you don't ever, I don't think I need any of those. All right, I should just do it sequentially. Just the lesson here. Okay, so I'm just going to go through all of these. Not going to go through my really successful classifier. I don't think I need to do that one. But I need to do this one. What's going on? So it's somehow taking, where is it saying, why does it think I should use, why is that my old one? Shouldn't that be my new one here? Where did I create X? Oh, I did it here. I see. Of course, the thing that I did it out of sequence again. All right, just do it fully in sequence this time. Okay. Now I think this should work. All right. So everyone see what I was doing there? I had overwritten my X features with the image ones. So I had turned a classifier to use both the image features and the other features, and I had overwritten something that I didn't mean to overwrite. And so I had to go back and reload everything to the point where I would have my original classifier that, let's just make sure that I can in fact get this level of performance. Oops, no, that's not good. Let's see, so this. Okay. Classifier is logistic regression. Boy, that's not good. This should be exactly the same. Huh, okay, well, I'll have to figure out what's going on there. I don't want to waste too much time debugging this at this point. It's still a reasonable classifier, but it seems worse. It definitely was worse than it was before, so I'm not quite sure why that is. Maybe did I pick like a random thing here? I don't know. Let's see. So this should be around that, so I'm not quite sure this is happening. Okay. Anyway, it won't change the actual results we get, other than making them marginally worse. So again, I've now knocked off a little bit more points. This is something like 0.75, as I recall. So you can maybe check out what's going on with that and figure it out. See if I missed something obvious here. Did I not do this? I don't know. Okay. Well, the wonder of non-deterministic performance here. Okay, so let's get my feature here. Let's call this X deploy. That was my whole. If I had just not done that, that would have saved everything. So let's call X deploy that thing. And now let's also evaluate my classifier on this new thing. So I can say classifier.score, or it's a decision function. This is the actual prediction it makes for each of these things on X deploy, and this is going to be my scores. So deploy scores. Scores equals this. Actually, before I do this, let me check one more time to make sure this is still. This is my classifier. Make sure this is still. Yeah. So it still is sort of the thing. Oh, maybe I didn't remove stop words or something like that. It's where the and is there. So maybe that was the issue. I didn't remove stop words. No, it's still the same. I don't know. Okay, so let's go and deploy this. Now we've created our scores on the deploy matrix, and I'm going to now set my the column here of say the score equal to these deploy scores. Okay. And so now the big question we're going to have is what are the top items that are unreviewed that actually are going to be the ones that we they're under-reviewed at least, they're going to be the top ones. So does anyone want to guess what the top items are going to be? Yeah. Yeah. Right. What are the worst items going to be? Yeah, exactly. So nothing too shocking here. The patterns we see in the test that are probably still going to be this, that we saw on the before are probably still going to exhibit themselves in this deployment set. So let's see anyway. Actually, going to say just sort it by values. By score and ascending equals false. And let's just look at the top, say 20 items. Let's look at their name. Okay, so a lot of Fisher-Price, Imaginext, Power Ranger. Remember, Fisher-Price and Imaginext were both good things there, and PACs were good. So not surprisingly, the best possible thing you could have is a Fisher-Price Imaginext PAC of some kind. That was just the thing. These are linear classifiers, remember, so the more each time you see a word like that, it's just going to bump up the weight, and so everything's going to be good. If you look at the bottom now, again, no real surprise here. The worst you could possibly do is, basically ducks and baths and toys, and I'm not quite sure. I guess maybe probably like spill is also going to be a bad word there. I think actually saying toy also has some negative effects. I believe that saying toy, I'm not sure why, but toy, maybe a little bit further down in our model, but I think toy, I recall, if I looked at it more, had negative effects too. So this is sort of, again, this is not surprising what you saw here, and as I said, I could have probably stopped the lecture after we looked at the feature names first. But it is also important, I think, to realize how you're going to once you've created your data set, how are you going to actually go about deploying it to some new classifier, some new data that you have never seen before, or you don't have the answers? The thing you do there is you cannot actually, evaluate these things in terms of any true value, though I bet, if you look at these ratings, on average, they would be, in fact, lower than the other ones, because people are not going to like bath toys no matter what. And people are probably going to like Fisher-Price stuff no matter what. But it's helpful to see not only how you apply to the data you've trained on and the cross-validation set in your test set, but also truly unlabeled data in some sense, right? So this data, as far as we're concerned, really is unlabeled. And it's the ones where you really want to understand, if not the accuracy, you want to qualitatively evaluate the predictions there to at least make sure it's jiving with your intuition about what it should be picking up on. And it does seem to be, in this case, picking up on the exact things it did before. And maybe if I am able to go back and use this one here, it'll probably be very similar, actually, on the top or the bottom, but maybe a little bit better. It'll pick up on some random image features that sort of give it a hint about what are the best and worst bath toys and best Fisher-Price toys, maybe, right? Okay, so this is actually all I'm going to do with this walkthrough. The basic points are sort of the following. Okay, so the basic points are, first of all, we talked a little bit, and this will all be online, so you can look at this notebook online, maybe figure out what on earth this is doing, was giving me before 7.5 and now 7. But the basic point here is that this kind of covers pretty much everything you need for a data science, a very simplified version, but kind of a data science project like this, right? And we just coded it all up in class. And yes, of course, I had a sheet, but this doesn't take me that much longer to write than the class time. Now, of course, I've also sort of done this a few times with different data sets, so I'm fairly fast at it. But it's the kind of thing you can do pretty quickly, right? So what did we do? We first started with scraping data, right, with an unknown data set that was trying to actively forbid us from scraping. We formatted it into some sort of database. I probably should have used an actual database instead of like writing it to a pickle file. That would have been actually quite a bit nicer and also showcased SQLite or things like that. So I would actually recommend using a real database. But I was lazy enough to do a pickle file, reloaded it, then loaded it into a data frame. Did some basic visualization of this data, so it's got a sense of like what the data looked like, what the different types of, what the different, how the ratings corresponded to price and to how many times they've been rated, things like that. Kind of made a modified version of ratings that seemed to make more sense given the fact that a lot of things weren't rated that often. Looked at sort of a first take on just predicting raw rankings, or raw ratings, which seemed, plausible, but didn't actually pan out that well. And this included things like doing transforms of the data, though, even at that level, to transform variables between 0 and 1 to variables that are much more Gaussian in nature. After doing that, we took a step back because we didn't seem to be doing all that great over a baseline with this. Started playing a game about this actual data. So can we actually even attempt to solve the task that we're trying to solve up there? Again, with the important point being, don't try to predict numbers if your class regression task. Try to predict relative rankings of items, because we are really bad at predicting numbers. We're much better at predicting binary decisions like that. We found out that we really couldn't do that, so we moved on to this, easier problem of just looking to see if was there any signal at all in the top and very, very top and very, very bottom of this list. And it seemed like there was. And it turned out that the signal is almost entirely about brand names and bath toys. But that's actually quite an interesting insight, I think, into the nature of what's happening in these reviews. We then also integrated image features in, and saw that they did worse than just the plain text, but the combination did marginally better. And if you are trying to really push the performance aspect of this, you probably would want to include both those things to get the best performance you possibly could. Then finally, we talked about how do you actually deploy these things to a unlabeled new data set. In this case, the ones that were not rated enough. And we got the best possible toy that I'm going to have to get now is going to be obviously this Fisher-Price Imaginext Power Rangers Battle Pack, which doesn't sound that great, really, but I guess I've kind of committed to it now, so maybe I have to go ahead and do that. Okay, so that's actually it for today. The last thing I'll do, I have a few minutes to spare, so the last thing I'll do is, now that everyone's here, well, not everyone, but a good number of people are here, let's open up this poll. The poll is, what will happen on that day? No, it's just the video. Remember, the assignment is you have to release you have to submit to a 90-second video. And that's a sharp limit, by the way. We'll have a section on how you do that. What you will do is you will upload it to yourself to YouTube and just submit the YouTube link for your group. That's how you'll do it. We cannot, if we tried to convert all the video file formats there are, it would be hopeless. We would never actually do this. So you will yourselves already upload it to YouTube. It can be public, or it actually has to be public, so we can use it in a playlist. It has to be public. You upload it to YouTube, but it can be unlisted. It doesn't have to be public. It can be unlisted if you don't want people to go out and find it. Could be public though, and you will. Then we will compile it into a big playlist, and we'll actually just sit down and kind of watch them back to all in one long stream, but we'll try to have pizza and stuff here to make it somewhat enjoyable, because otherwise a pretty long experience. The question is, do you want to do that at 8:30 in the morning or 8:30 at night? I guess actually, you know what? Let me actually add a third option, which is so earlier in the evening, which is around like 6 p.m., but in separate rooms. So we have to actually have like 2 different satellite rooms, each playing its own playlist then. And in that event, yeah, you have to sort of do this it wouldn't be quite as fun if we're not all in this room. This room, for example, is not open right then. Okay, so let me actually do that, and let's go ahead and open the poll and see what people say. Totally split amongst them. Though there seems to be some preference for later in the evening as opposed to earlier. Though with the caveat being that this is actually the default time. But still 24%. What I'm going to do is I'm going to leave this poll open, and people also online can in the class can answer it. I guess you have to, it means like, you didn't actually have to show up to class today even with a poll. I think I get a timestamp of when you answer it too, so I actually know. Okay, so we'll decide about that. I'm looking for a room that can fit us all in the evening sometime. I don't think there is any that can fit everyone in the class, but hopefully at least a lot of us in the class. And And I tend to think it's more fun to have, you know, pizza and be awake than have to be drinking coffee and have that. But we'll have either one, either way. So we'll send out an announcement. It'll be this week that we decide, but regardless, it doesn't change when your things are due. Your things are still due the night before at midnight, your videos. And we'll post a link on that.